Hi! In this lesson, we will discuss the problem of organizing children into groups. And you will learn that if you use a naive algorithm to solve this problem, it will work very slowly, because the running time of this algorithm is exponential. But later, in the next lesson, we will be able to improve that running time significantly by coming up with a polynomial time algorithm. Let's consider the following situation. You've invited a lot of children to a celebration party, and you want to entertain them and also teach them something in the process. You are going to hire a few teachers and divide the children into groups and assign a teacher to each of the groups. This teacher will work with this group through the whole party. But you know that for a teacher to work with a group of children efficiently, children in that group should be of relatively the same age. More specifically, age of any two children in the same group should differ by at most 1 year. Also, you want to minimize the number of groups, because you want to hire fewer teachers and spend the money on presents and other kinds of entertainment for the children. So, you need to divide children into the minimum possible number of groups, such that the age of any two children in any group differs by at most 1 year. Now let's look at the pseudocode for the naive algorithm that solves this problem. Basically, this algorithm will consider every possible partition of the children into groups and find the partition which both satisfies the property that the ages of the children in any group should differ by at most 1 and contains the minimum number of groups. We start with assigning the initial value of the number of groups to the answer m, and this initial value is just the number of children, because we can always divide all the children into groups of 1, and then of course each group has only 1 child, so the condition is satisfied. Then we consider every possible partition of all children into groups. The number of groups can be variable, so this is denoted by a number k, and we have groups g1, g2 and up to gk. And then when we have a partition, we first need to check whether it's a good partition or not. So we have a variable good, which we assign to true initially, because we think that maybe this partition will be good. But then we need to check for each group whether it satisfies our condition or not. So we go in a for loop with index I of the group from 1 to k, and then we consider the particular group gi, and we need to determine whether all the children in this group differ by at most 1 year, or there are 2 children that differ more. To check that, it is sufficient to compare the youngest child with the oldest child. If their ages differ more than by 1, then the group is bad. Otherwise, every 2 children differ by at most 1 year, so the group is good. And so we go through all the groups in a for loop. If at least one of the groups is bad, then our variable good will contain value false by the end. Otherwise, all the groups are good, and the variable good will contain value true. So after this for loop, we check the value of the variable good, and if it's true, then we improve our answer, at least try to improve it, with the minimum of its current value and the number of the groups in the current partition. And so by the end of the outer for loop, which goes through all the partitions, our variable m will contain the minimum possible number of groups in a partition that satisfies all the conditions. It is obvious that this algorithm works correctly, because it basically considers all the possible variants and selects the best one from all the variants which satisfy our condition on the groups. Now let us estimate the running time of this algorithm. And I state that the number of operations that this algorithm makes is at least 2 to the power of n, where n is the number of children in C. Actually, this algorithm works much slower and makes much more operations than 2 to the power of n. But we will just prove this lower bound to show that this algorithm is very slow. To prove it, let's consider just partitions of the children in 2 groups. Of course, there are much more partitions than that. We can divide them into 3, 4, and so on, much more groups. But let's just consider partitions in 2 groups and prove that even the number of such partitions is already at least 2 to the power of n. Really, if C is a union of two groups, G1 and G2, then basically we can make such partition for any G1 which is a subset of such C of all children. For any G1, just make group G2 containing all the children which are not in the first group. And then all the children will be divided in these two groups. So now, the size of the set of all children is n, and if we want to compute the number of possible groups G1, then we should note that each item of the set, or each child, can be either included or excluded from the group G1. So there can be 2 to the power of n different groups G1. And so there are at least 2 to the power of n partitions of the set of all children into groups, and it means that our algorithm will do at least to the power of n operations because it considers every partition, and among all the partitions there are all the partitions into two groups. So how long will it actually work? We see that the naive algorithm works in time omega of 2 to the power of n, so it makes at least 2 to the power of n operations. And for example, for just 50 children, this is at least 2 to the power of 50, or the large number which is on the slide. This is the number of operations that we will need to make. And I estimate that on a regular computer, this will take at least 2 weeks for you to compute this, if this was exactly the number of operations that you would need. So it works really, really slow. But in the next lesson, we will improve this significantly.